Now that we've learned about electrochemical cells and calculating cell potential, we can relate the potential back to other thermodynamic values that we have studied. So free energy can be related to the potential with this equation, delta G equals negative times NFE, where N is the number of electrons in the balanced chemical equation. F is Faraday's constant, which is 96,485 joules per volt mole, or coulombs per mole. You'll need those units to help you cancel out in the math. And then the cell potential that we have studied. So if we have an equation for delta G, and we have other equations for we have an equation for delta G that relates it to the cell potential, but we also have equations that relate delta G to the equilibrium constant. So if we set these equations to each other, we can rearrange and find a relationship between the cell potential and the equilibrium constant. So now we have the cell potential is equal to R times T over N times F, and that is times the natural log of K. Some of these numbers tend to be constants, so you can use the full equation, but if you have the standard temperature of 298 Kelvin, and we go ahead and cancel out all the related units, you can have a more abbreviated equation that looks like this, or just plug in the values so you don't have to worry about whether the temperature is standard or not. But that is how the units would cancel. We also have a nice triangular relationship here that relates the cell potential, the equilibrium constant, and the free energy. So now you have two equations to find each value. So delta G can be found through the cell potential or an equilibrium constant. The cell potential can be found through delta G or the equilibrium constant, and an equilibrium constant can be found through the cell potential or delta G. All right, so let's work an example. What is the equilibrium constant and the free energy for the following reaction at 25 degrees Celsius? All right, so let's evaluate this equation. We want to, in this chapter, we are studying cell potential, so let's relate these values to the cell potential. The oxidation half reaction is the silver being oxidized to silver plus. The reduction half reaction is the iron 2 plus being reduced to iron. And in the balanced equation, we see that there are 2 electrons being transferred, so N is equal to 2. If we look up the values for the standard potentials for the iron electrode and the silver electrode, we find that the iron is negative 0.44 and silver is positive 0.8. So with cathode minus anode, we get a negative 1.24 volts. We already know that a negative potential indicates a non-spontaneous reaction. Now let's go and calculate the delta G, or I'm sorry, the equilibrium constant. So if we take this equation and rearrange it to solve for K, we get K is equal to the exponential of the cell potential times NF over RT. So if we plug all those numbers in and do the calculation, we will get 1.138 times 10 to the negative 42. This is small. It's less than 1. Much less than 1. So that means that it favors the reactants. Again, not a spontaneous reaction. All right, let's calculate delta G. So technically we're calculating the standard delta G. It's related to negative NFE. So we've already calculated the standard cell potential, so we can plug in our values. Don't forget your negative. The number of electrons was 2, and we have 96,485, and the cell potential was negative 1.24. So we get a positive 239,000 joules, or 239 kilojoules. Again, positive means non-spontaneous in terms of delta G. So all three of these values are consistent. The negative potential, the positive free energy, and the very small k tell us that the reaction is not spontaneous as it is written. As you work examples in this unit, you will find that your calculator may give you errors and not perform some of these calculations, especially with numbers getting even smaller than times 10 to the negative 42. So if your calculator gives you errors, then just have Excel open and run the same calculation in Excel, and it can perform the calculation and give you an answer. All right, so here is just a quick summary of all the values we've looked at and how they relate to spontaneous or non-spontaneous reactions. Remember that delta H and delta S did not tell us whether the reaction was spontaneous, but it did tell us whether it favored spontaneity or not. So a negative delta H, an exothermic reaction, is favorable, whereas the positive was an endothermic reaction, is not favorable. And for entropy, positive was favorable, whereas negative was not. And then with delta G, we get to something that actually states whether the reaction is spontaneous. Negative is spontaneous, positive is not spontaneous. And we have learned in this unit that potential, the cell potential, positive potential means that it has voltage that can go and do work, so that is spontaneous, and a negative potential is not spontaneous. And in terms of equilibrium, a value larger than 1 favors the products, so it's spontaneous in the forward direction, and a negative, K cannot be negative, but a small value less than 1 means that the reactants are favored. So it's a non-spontaneous reaction.